Hello everyone, I hope you're all in good health. Welcome to the presentation of our ICASSP 2020 paper titled Exploiting Periodicity Features for Joint Detection and DOA Estimation of Speech Sources Using Convolutional Neural Networks. My name is Reza Varzandeh and I am an R&D engineer at Hohmann Oldenburg and also a PhD student at the University of Oldenburg in Germany. It's my pleasure to present this joint work authored by me and Adiloglu from Hohmann Oldenburg and Doclo and Hohmann from the University of Oldenburg. In this work, we refer to the DOA estimation as estimation of a sound source direction of arrival with respect to a microphone array. Reliable DOA estimation is essential to many applications such as assistive listening devices, hands-free speech communication systems, and robot audition. While the human auditory system has the remarkable ability to localize a speech source in noisy and reverberant environment, this remains a challenging task for machine listening systems such as hearing aids. Classical DOA estimation methods such as generalized cross-correlation and also steered response power with phase transform have been commonly used over the years. However, their performance degrades in noisy and reverberant environments, and they all need manual parameter adaptation. In contrast to these methods, the learning-based approaches during the training phase can learn a mapping from the signal features to the DOA of sound sources, and thereby can be adapted to different acoustic conditions. Among these approaches, the deep neural network-based methods, the so-called DNN-based methods, have been shown to be more robust against noise and reverberation. However, most of the aforementioned DOA estimation methods do not take the speech activity into account. To avoid estimation errors merely due to inactivity of speech, the voice activity detector is usually used as a cascaded or parallel system with a DOA estimation system, which requires itself manual and time-consuming parameter tuning. In this work, a hybrid convolutional neural network is proposed, which exploits a novel feature combination for joint speech detection and DOA estimation in the context of binaural hearing aids. GCC-FET has been widely used as a robust feature for DNN-based DOA estimation methods, and it has been used in this work as the input feature for the baseline CNN, which is called the GCC-CNN. In our proposed hybrid CNN, which is called PD-GCC-CNN, we utilize a novel feature combination. In addition to the well-known GCC-FET feature, the proposed network uses an auditory-inspired feature called periodicity degree, which provides a broadband representation of the periodic structure of the signal. In this work, we consider a binaural hearing aid setup with 4 microphones, where each microphone signal receives a single source signal and an uncorrelated background noise signal. At each time frame n, the GCC-FET feature vector for each microphone pair of the binaural hearing aid setup is estimated by taking the inverse Fourier transform of the cross-power spectrum phase between the 2 microphones, and then limited to the maximum possible delay between the 2 microphones. At each time frame, the GCC-FET feature vector for our considered binaural hearing aid setup is constructed by concatenating the GCC-FET feature vectors for all 6 microphone pairs, specified in this image by the green box, where peaks in the concatenated feature vectors can be identified as yellow data points. Finally, feature vectors of multiple consecutive timeframes are used as the 2-dimensional input feature map. At 16 kHz sampling frequency with SDFT frame lengths of 10 milliseconds with 50% overlap and the Hahn window, in total, we got 678 GCC-FET feature in each time frame for all 6 microphone pairs. It is well known that the human auditory system groups signal components according to information such as harmonicity, and then interaural time difference information is used to segregate them. This motivates using the periodicity information in combination with GCC-FET as input features for joint voice activity detection and DOA estimation, which is one of the main novelties in this work. Periodicity degree, which captures the harmonic content of the signal, has been shown to be useful for voice activity detection. Given a set of capital N number of period candidates, The PD feature vector at time frame n is defined as the ratio of the harmonic signal power for each given period and the total signal power. Here we note again that the network needs feature map of a block containing current and past frames. By choosing n equal to 180, the range of fundamental period candidates for PD feature extraction lies between 3.1 milliseconds to 14.3 milliseconds. I would like to illustrate an exemplary representation of PD for clean and noisy speech and also engine sound as non-speech signal. While for the PD example, for the speech examples, the fundamental period and its multiple harmonics can be identified as a two-dimensional structure over time, no such harmonic structure can be found for the engine sound. We propose to formulate the joint DOA estimation and voice activity detection task as a C+1 class classification problem, where the first classes, C classes called DOA classes, refer to all possible discrete DOA values, and the last class called detection class refer to the non-speech activity. In this work, the full 360-degree azimuth range is discretized into 72 directions, which correspond to a 5-degree resolution DOA map in the horizontal plane. Considering the exemplary representation of the PD feature in the previous slide, the proposed CNN is expected to learn the harmonic structure and continuity of the sound source from the PD feature map, and thereby discriminating between the speech and non-speech blocks, and at the same time capture the spatial information of the sound source from the GC-CFAT feature map, thereby finding the DOA. Now let's move on to the proposed network architecture. The proposed network consists of two independent branches of cascaded CNN layers. The outputs of both branches are concatenated after a flattening layer and then used as input to a cascaded fully connected layers. Except for the output layer where a softmax activation function is used, the ReLU activation function was utilized for all convolutional layers and also the fully connected layers. The proposed system and also the baseline system, which has not been discussed yet and soon will be discussed, were both trained for two different block lengths specified as L. We propose to train a hybrid CNN in a single label multi-class classification scheme where each label is one-hot encoded. It means that each training example belongs to only one output class. For training feature map of a speech source coming from a certain direction here, 0 degree, plus 5 degree, and plus 10 degree, the DOA class corresponding to that direction is labeled by 1, while the other classes, including the detection class, are labeled all by 0. However, for a training feature map of a non-speech source, the detection class is labeled by 1, while all DOA classes here are labeled by 0, no matter which direction the non-speech source is coming from. It is important to note that in the proposed system, we do not aim at voice activity detection, but we expect the proposed CNN to only estimate the DOA of a sound source when speech is detected. For the classification now, under the single source assumption and given a predicted probability map at the output, we take the largest value of the probability map. Then, if the detection class is found as the maximum, our estimate in that block is detected as non-speech, and hence we do not estimate the DOA. Otherwise, speech is detected and the detected class determines the estimated DOA. The performance of the proposed CNN is compared with a CNN which only receives the GC-CFAT features as input, as it is merely designed for DOA estimation. This baseline CNN looks very similar to the upper branch of the proposed CNN. And during the classification of the baseline system, for a predicted probability at the output, the estimated DOA is determined by the DOA class, which has the largest probability at the predicted output. For training and validation, we use 300 and 100 speech and non-speech sound sources from TIMIT and ESC50 datasets. The clean binaural microphone signals used during the training were generated for both speech and non-speech sources by convolving them with anechoic binaural room impulse responses. Then the noisy microphone signals at different SNRs from -10 dB to +20 dB were generated by mixing the clean binaural signals with the simulated binaural diffuse noise. Both the proposed and baseline systems were evaluated in two different reverberant environments. For speech sources where 150 unique speakers, each with the length of 1 second, were randomly selected from the validation TIMIT corpus. Recorded cafeteria babble noise and courtyard ambient noise were used to generate noisy binaural microphone signals at different SNRs, from -5 dB to +10 dB. In each environment, 4 source positions, each with 2 head orientations, were considered for the evaluation. We used 2 metrics, accuracy and mean absolute error, to evaluate the DOA estimation performance of both the proposed system and the baseline system. An estimate is considered accurate if the absolute error between the estimated DOA and the Oracle DOA is smaller than 5 degrees. As no voice activity detection is integrated into the baseline system, it is evaluated for all signal blocks labeled by the Oracle VAD as speech in the evaluation data. And on the other hand, the proposed system is only evaluated for signal blocks which labeled as speech by the Oracle VAD and also predicted as speech by the proposed system. Now let's discuss the evaluation results. In this figure, the performance measures of both methods in terms of accuracy here and mean absolute error for different SNRs in 2 different reverberant environments were shown for 2 block lengths of 100 milliseconds and 250 milliseconds. The performance measures of the proposed method are color-coded in 4 different SNRs, while the white narrow bars show the performance measures of the baseline method. For both environments, the proposed method clearly outperforms the baseline method, both in terms of accuracy and mean absolute error, and particularly for low SNR conditions. The benefit of joint estimation is more prominent for smaller block lengths. This can be explained by the fact that when using a smaller block length, the proposed network correctly classifies more blocks with little speech activity and dominated by noise as non-speech blocks. So the better performance of the proposed method for shorter block lengths can presumably lead to better tracking performance for moving sources. In a recent evaluation, which was not prepared at the time of the ICASSP paper submission, an unsupervised segment-based method for robust voice activity detection called RVAD is integrated into the baseline system here, which enables the baseline system to detect signal blocks dominated by noise and thereby discarding them from the performance evaluation of the DOA estimation. The whole evaluation scheme here is similar to that of the paper, except for using the RVAD in the baseline system. In the new evaluation results, it can be observed that the performance of the baseline system improves both in terms of the accuracy and mean absolute error. However, for both environments, the proposed method still outperforms the baseline method, more particularly at low SNR conditions. Concluding my talk, we propose the hybrid CNN architecture for joint DOA estimation and VAD in a single talker scenario by exploiting both GCC FET features as well as an auditory-inspired periodicity degree. Based on our results we discussed, particularly in the low SNR conditions, the proposed hybrid CNN outperforms the baseline CNN. The proposed method is able also to adapt to different acoustic conditions and also the unseen background noises. Thank you very much for your attention, and I would be very glad to answer any questions you might have.